Hello everyone, welcome to our discussion of section 6.2 where we will be talking more about integration techniques. Now if you can see, if you see me wearing these sunglasses, it's because this fine document camera that I'm using has a very bright background plate. So I'm using this to reduce the glare into my eyes, but that's the only reason. So in this section, the first thing we will talk about is how to integrate the powers of sine x and cosine of x, powers that are, of course, higher than 1. So case 1, we will look at, so this being the main topic of this portion of the lecture, case 1 of this will be when the power of cosine of x is odd. Any odd power, 3, 7, something like that. So in this case, we always want to save one cosine factor and we'll do plenty of examples so you'll see exactly how this works. Say one cosine factor and use one of the squared identities, squared trigonometric identities that we've learned back in trigonometry course, and use cosine squared x equals 1 minus sine squared x. In terms of sine x. Okay, then after we've done that, then use u equals sine x for substitution. Okay, so let's do an example right away to see how this works. Well, let me, even though there's significant portion of this page left, let me just say see the next page because I want to make sure that I can fit the whole solution on one page. So see the next page. And I'm going to be posting these lecture notes on Canvas so you can access them if you want to. So here's the example we have. We want to integrate an expression from 0 to pi over 2. So this is a definite integral of sine 7 theta, sine to 7 power theta, times cosine to the 5th power theta d theta, right? Right away you notice that this is the case we're talking about. That when the cosine factor and when the cosine of x has a power that is odd. Okay, so that fits that. Okay, so what we said is that we want to save one factor of cosine of theta, right? So save one cosine factor. So let's do that. So here's the solution for that. So we have integral from 0 to pi over 2 times sine to 7th power theta, then cosine to 4th power theta times cosine theta d theta, right? We just broke this cosine to the 5th power to cosine to the 4th times cosine theta d theta. Then after that, we can rewrite this in terms of cosine squared theta is squared, right? So let's do that. So notice that I'm keeping the sine to 7th power theta intact so far. So cosine squared theta squared cosine theta d theta, right? So far we've just been rearranging these terms as prescribed in this technique. Then we know that cosine squared theta is equal to 1 minus sine squared theta, right? Again, we know that from trigonometry. And I'll just remind you here, knowing that cosine squared theta is equal to 1 minus sine squared theta, then we can substitute for this with 1 minus sine squared theta. So let's do that. And we have sine to 7th power theta times 1 minus sine squared theta squared cosine theta d theta, right? Now that we have figured this out, then we need to substitute as it said, then use u equals sine of x. So let's do that. So we're going to say let u equals sine theta, because we're using theta instead of x. As soon as you make this substitution, then you'll have to calculate du, right? So du, find the derivative of this. Derivative of sine theta is, of course, cosine theta d theta. Do you see something similar with respect to this and that? Cosine d theta equals du. So all of this can be set equal to du. But before we proceed with that, notice that this is a definite integral. Whenever we have a definite integral, we need to recalculate, and we're using a substitution method, we're going to need to recalculate these limits with respect to the new variable u. So if theta equals 0, let's say, and substitute that, what do we get? Sine of 0 is going to be 0. So u is going to be equal to 0 as well. If theta is equal to the upper limit of the integral, which is pi over 2, then sine, according to this substitution equation we've picked, sine of pi over 2 is just 1, right? So u equals 1. So our new limits of integration for the new variable u is from 0 to 1, rather than 0 to pi over 2. So now we're going to be able to rewrite this integral in terms of the new variable u. So we have equals 0 to 1. Since we picked u to be sine theta, then it's really easy to rewrite sine to the 7th power theta as u to the 7th power, right? U to the 7th power times 1 minus, this is sine squared theta, so 1 minus u squared, and then cosine theta d theta, as we found out earlier, it's equal to du, so du. So after that, this is a very simple, becomes a very simple expression to integrate. Let's do that. So we have, well, first let's expand this binomial and then distribute the u to the 7th power into it. So what we have is 0 to 1, u to the 7th power times 1 minus 2u squared plus u to the 4th power, right? du. Now I'm going to distribute this. And so what do we have? Let me move this up a little bit. So we have 0 to 1, u to the 7th, minus 2u to the 9th power, plus u to the 11th power, right? This distributed to that. The bases are the same, so we add the powers, and of course, let me put the parentheses, du. All right, so now we can easily integrate this. We will have this add 1 to the 7th, divide by the new power 8. So we will have 1 over 8 times u to the 8th. This one, add 1 to 9, we get 10, divide by the new power 10. Minus 2 over 10, we can simplify that to minus 1 over 5, u to the 10th power. add 1 to this power, divide this term by the new power 12. So we get 1 over 12 u to the 12, like that. And of course, we close the bracket and then 0 to 1. Okay, so now let's apply the limits to this variable u. Notice, by the way, that when we have a definite integral, we don't have to convert this new variable to the old variable. If we have an indefinite integral without these limits, then we'd have to, we'd get the c, of course, plus c, the unknown constant, but then u itself would have to be converted back to the original variable theta. But in this case, we don't do that because we have a definite integral here. Okay, so I'm just going to substitute. We get 1 for every u I see in this expression. So we get 1/8 minus 1 over 5 plus 1 over 12. And then 0 will make all of these zeros. So all of this minus 0 plus 0. So it just, I just wrote it just to be sure that everyone is following what's happening. But that whole thing drops out. So then we take the common denominator of what we have, and that would be 120, and then so we have 15 here. This is just basic algebra I'm doing, plus 10, and we should get 1 over 120. So this is our final result for this definite integral, right? Of course, that's what we would expect for any definite integral. We would expect a number like that, a scalar. Okay, so let's look at other cases and other examples here. All right, so that was, which case was that? So that was case 1. So this was case 1 when, of this scenario, how to integrate powers of sine x and cosine x. Later on, we get to how to integrate powers of tangent of x and secant x. Okay, but these are the cases relevant to this situation when we have powers of sine of x and cosine of x as factors. Okay, so case 2 of that is when the power of sine of x is odd. That was when the power of cosine of x was odd, right? So now when the power of sine of x is odd. Okay, sine of x. Okay, in this case, here, we want to save one sine factor. So save one sine factor. Last time, when power of cosine of x was odd, we saved one cosine factor, right? Here we want to save one sine factor and use the same squared identity from trigonometry. Let me write that again. This time, sine squared x equals 1 minus cosine squared x. To express the remaining in terms of cosine of x. After that, of course, we want to use u. That last time we used u equals sine of x, so we now use u equals cosine of x. Okay, so let's use an example to demonstrate how this works. So suppose we want to integrate. By the way, this technique could apply to this example too. Let me bring this back, because we're now discussing when the sine factor, when the power of sine of x is odd, right? So in that technique could be applied here as well, because sine here has an odd power as well. So just so we could use this technique there too, we'd get the same thing. So in this example, we have sine cubed theta times cosine to the fourth power theta d theta. Okay, so the solution for this case would be as follows. I highly encourage you to pause the video at this point and spend 10-15 minutes max, write down your solution, and then come back to the video. This will hugely impact how fast you're going to learn this, and rather than just watch me go through the procedure from start to finish right away. Okay, so I highly encourage you to do that. All right, so I'm assuming you've done that, and now you're back. So according to what this procedure is saying, we want to save one sine factor. So I'm going to break this sine cubed theta into sine squared theta times sine theta. Okay, so let's do that. So we have, and notice that this is an indefinite integral. So at the end, we're going to have to convert back to sine and cosine. We can't use u to finish this off, okay, because this is an indefinite integral. So sine squared theta times cosine to the fourth power theta, and then the one sine that I took away from here appears here, sine theta d theta. Then we know that, again, knowing from basic trigonometry, knowing that sine squared theta is equal to 1 minus cosine squared theta, right? Math 127, if you've taken that course here. So we'll have 1 minus, I'm just substituting for that, 1 minus cosine squared theta times cosine to the fourth power theta, and then sine theta d theta. And of course, at this point, we want to pick our substitution variable. So let u this time equal cosine of theta. As soon as you pick that for your new variable, then you have to calculate du. You have to calculate the, because we had d theta for theta, so we need du for u, and that is equal to, du would be equal to minus sine theta d theta. And so that, and let's see, so we have, and yes, so like that, and now we can substitute in this from here. All right, so we have this minus. Let me put that up front, because we're going to substitute for that, for cosine theta with u. So we end up with, so that minus you see here is that. So that appears here, or you might as well write it like this, or you can either leave it like that and make that minus appear here, or you can write it like this, minus du equals sine theta d theta. So sine theta d theta equals minus du, and that minus appears here. Either way is fine. So then, substituting back here, we have 1 minus u squared. On the outside, we have cosine squared squared. So that'll be u to the fourth power, right? Because cosine theta is u. So cosine to the fourth power, that would be u to the fourth. And then, of course, sine theta d theta will be the du, and the minus is out here. So we have du. All right, so now let's let us distribute this and integrate. So we have minus u to the fourth times 1 is u to the fourth, and I'm going to put the parentheses here. And then u to the fourth times u squared is u to the sixth, and then we have, of course, du. And then that, or of course, then we can distribute this into that and simply write, we can distribute this minus into that and get rid of it and make it part of the integrand, and we can write positive u to the sixth minus u to the fourth du. Okay, then now that's minus is part of the integrand. And then, so now we can integrate. Let's add 1 to this, divide by this term by the new power 7. So 1 over 7 times u to the 7, of course, minus add 1 to this, divide this term by the new power 5. So 1 over 5 u times u to the fifth power. And of course, this is the indefinite integral. So what are we going to get? We're going to get plus c, that unknown constant. So again, as I said earlier, because this is an indefinite integral that we were working with, so the final result, we cannot leave it like this. We need to convert this new variable u to the old one. And we know what that is, right? It was u, we took that as cosine theta. So we're going to substitute back with cosine theta wherever we see the u appear. Okay, so that is equal to 1 over 7 cosine 7x. Oh, well, in this case, we had theta. So, sorry, let me change that to theta. Cosine to 7th power theta. Sorry for that. And then minus 1 over 5 times cosine to the 5th power of theta plus c. Okay, so that's that. And of course, I just want to remind you that, let me remind you something that I said earlier. Note, this method could have been used with case 1. With case 1, okay? Like that. All right, so now, so that was our case 2, I believe we called it, right? Case 2, so case 3. So case 3, that's when powers of sine and cosine were odd. So what about if they're even? So when powers of both sine and cosine, these two guys, are even. Okay. So here we'll have to use the half-angle formulas. Again, this is going back to the basic trigonometry. So we will use here the half-angle formulas, and I should say not only these, but any other identities that might be, any other identities or creative ideas. So let me add that too, because they also can be used. So this is a crucial piece of this, the technique for integrating powers of both sine, when powers of both sine and cosine are even. But also, let me add, and other trigonometric identities or ideas that may be creative and helpful. Okay, so that's the bit. But of course, let me highlight that piece where we're using the half angle formula. So I'll just highlight that piece. And then, of course, that comes with it too. Okay, so let's go through an example. Suppose we want to evaluate this integral. So, and it's again a definite integral from 0 to pi over 2. And this is sine squared x cosine squared x dx. So note that we can rewrite this, and by the way, so again, it's really worth your time to pause the video and give this a shot for 10-15 minutes. Just give it your own thought and thinking, and then come back to the video. So I'm assuming you've done that, and now you're back, which is great. So I hope you went all the way and solved this. If not, that's not a problem at all. Since you've given it your thought, that's what counts. And so notice that we can rewrite it in terms of sine x cosine x squared, right? So we can do that. So let's do that. 0 to pi over 2 sine of x cosine of x times cosine of x squared dx, right? And the other thing that we need to, one of the other trigonometric identities that can be helpful, remember the double angle for sine 2x, formula for that? Sine 2x is equal to 2 sine x cosine x, right? But of course here the 2 is missing. But we can handle that. Remember when we used the method of squared in order to find the equation of an ellipse, to square an equation, to create a perfect square from an equation. We added a term and then we subtracted, but the byproduct was this perfect squared binomial. We can add things as long as we take care to eliminate that same term that wasn't there before. We can do that. So let's use that technique here, but before that, let me say that recall that sine 2x is equal to 2 sine x cosine of x. Compare that with that. Of course, this 2 is extra, but we can easily handle that. We can introduce it and then we delete it. And the benefit of that is that we get an expression that has no power. It's just sine 2x. Okay, so now we will do, so let's 0 to pi over 2, because so I'm just going to put that here. If I put 2 sine, I'm just going to replace this with 2 sine x cosine x, because I want to convert the inside to sine 2x, but this is being squared. So 2, the additional 2 that I introduced is going to end up coming out as 4, right? So if that's the case, I need a 1 over 4 out here to get rid of that 4 that is unnecessary, right? So that's how we get rid of it. We get rid of that 4 that is a product of this 2 squared. Okay, so that, and of course dx. And then what else? I think I should double check this really quickly. Everything looks good. Okay, so now we can write 0 to pi over 2, 1 over 4, and now I'm going to do what I intended from the beginning and rewrite this as sine 2x. And so sine 2x, so kind of, okay, we can handle that with a half angle formula later. So, okay, so that, and then dx, okay, so like that. And now let's distribute this power into this, what we have on the inside. So we have 0 to pi over 2 and 1/4. I should maybe put 1/4 out in front, but it's okay. And times sine squared 2x dx. Right? Now we can use the half angle formula, right? So recall that sine squared x, without the 2x that is, so just sine squared x is equal to 1 minus cosine 2x over 2. But of course, here we have a 2x, not x. So this 2 multiplies that 2, we get a 4x for our integral. But this is the original identity we're using in this case. Okay? So therefore, we have from here, we can write 0 to pi over 2, 1 over 4 times 1 minus cosine of 4x, of course, because we have 2x here, divided by 2 dx. Okay. All right. So now we have this 1/2 here. We can factor this 1/2 from this whole expression. Factor out 1/2, multiply it by this, and we can write 1 over 8, right? 1/2 times 1 over 4, 1 over 8 times 0 to integral from 0 to pi over 2 of 1 minus cosine of 4x dx. And of course, this is an easy expression to integrate. 1 simply integrates to x, and cosine of 4x, or minus cosine of 4x, integrates to minus 1/4 sine 4x. Right? By the chain rule, we get, if we take the derivative of this, we get a 4 out too. 4 times sine of minus sine of x. So we need, when we integrate this, we need to have a way to get rid of that 4. So we end up with just minus 1. So we have 1 over 8 times, integrate 1, what do you get? You get x. Integrate minus cosine 4x, we get minus 1 over 4 sine 4x. And of course, this goes, the limits of the integration are from 0 to pi over 2. Okay. All right, so let me, I'm running out of space here. So this would be equal to, I think I can put the rest of the solution here, over here. All right, so we get 1 over 8 times, so 0, well, let me just write it down, write it out. So we have pi over 2 for x, minus sine of pi, 4 times pi over 2, that's going to be 2 pi, which is 0, so minus 1/4, I'll just write it out and then simplify it later, like that. So this, after you put pi over 2 here, you get sine of 2 pi. And then, of course, substitute 0 for x, and this here, you get 0. So minus 0, close bracket. Okay. Now, more simplifying, we have 1/8 times, this piece is just going to drop out as well. That's 0. So we're going to end up with 1/8 times pi over 2, and finally we end up with pi over 16. okay, which is that. All right, so that's that. Did I write? So let me, I think I forgot to, I want to also, when I said we will use half-angle formulas, I didn't list them. So let me just give the two here. So for sine squared x, that is equal to 1 minus cosine 2x over 2. Because we have the tangent, the half angle for the tangent function, and of course for the cosine squared x, we have the 1 plus cosine 2x over 2. Yeah, I meant to rewrite these there, but since I forgot, I'm just listing them here. Okay, but you've seen these before in previous classes, and even in Calculus 1, I'm sure you've seen these. Okay. So next, let's see. So we talked about odd and even powers of factors of integration when there's sine and cosine. Now we want to talk about tangent and secant, of course. So this would be, so the main topic is how to integrate powers of tangent x and secant x, right? These two guys. Okay, so we want to, I want to underline that. That's our main. And what did we do? That was case 3. So I want to say, let's call this case 4. So case 4, we say case 4, if the power of secant x is even. Power of secant x is even, then save, we want to save a factor of secant squared x and use the other squared identities we have from trigonometry. And there were 3 of them, right? They're extremely useful in calculus. So secant squared x, it would be 1 plus tangent squared x. We're going to use that. And in terms of tangent x. And then we want to use tangent of x. Okay. So let's see examples of this. So we want to do, let's do this example. Tangent squared theta secant to the 4th power theta d theta. Okay, we want to do that. Okay, so obviously here the power of secant x is even, so we want to save a factor of secant squared. So let's do that. We're going to break this secant to the fourth power to secant squared theta times secant squared theta. Again, I highly encourage you to pause the video and spend 10-15 minutes on this and come back to the video to compare your solution with this. Okay, so equals tangent squared theta times secant squared theta times secant squared theta, right? We're breaking this up in d theta. And then we want to let, and by the way, this is an indefinite integral. So at the end, if we use a substitution method, we're going to have to convert back to the original functions or variables, theta. Okay, just keep that in mind. So now for this piece, we can substitute secant squared theta, of course, with 1 plus tangent squared theta, or tangent squared theta plus 1. Okay, so let's do that. So recall that secant squared x equals tangent squared x plus 1. So I'll just write it in terms of x, and then, because this is the general form, and then we'll apply it to this case. And then so we have tangent squared theta times, of course, tangent squared theta, we're substituting for this, plus 1 times secant squared theta d theta. We're keeping this secant squared theta d theta for when we pick our new variable u, and we have to take the derivative of that, and you'll see why we're keeping this. So it has a very good purpose, and I'm sure by now you're getting a hang of this, why we're keeping this piece until this point. So now we want to let u equals tangent theta. As soon as you pick this new variable, then you have to calculate du, or derivative of it, which would be, for tangent theta, it would be secant squared theta d theta. D theta. So compare this with that, right? It's du, right? So we can just substitute the whole thing with du. It's wonderful. So now we can convert to the new variable. This would be u squared, and inside would be u squared plus 1, and all of that is du. Okay, so let's distribute and integrate. We have u to the fourth plus u squared du, and this is really easy to integrate. So we have, add 1 to this, divide this term by the new power 5, so 1/5 u to the fifth, plus add 1 to that, divide this term by the new power 3, so 1/3 u cubed plus c, right? Because we are integrating an indefinite integral. All right, so now, because this is an indefinite integral, we can't leave it like as with u. We need to go back to the original term. We used u for. So wherever we have u, we're going to substitute tangent theta for it. So with that, we have 1/5 times tangent to the fifth power theta plus 1/3 times tangent cubed theta plus c, of course. Okay, so here's our antiderivative of that expression. Now, this was case 4 for how to integrate powers of tangent x and secant x when they're factors of each other, when they appear as factors inside in an integral. Now, case 4 was that, but case 5 is an additional piece of this case, but also for other cases. So we have to discuss all of those together. Case 5 and other cases, I'll call them like that. So this case 5 case 5 plus other cases. Okay, this is very important. So we said here if the power of secant of x is even, that was case 4. Now what about, so here if the power of tangent of x, this time that's our focus, tangent of x, is odd, then we want to save a factor of secant x tangent x, this product. Remember what this is? This is the derivative of secant x. Take the derivative of secant x, you get secant x tangent x. Okay? And use and then, so in terms of secant x, and then we want to use, yes, so let's use u equals secant x, and in case 4 we used u equals tangent x, and so use that, and then let's see, use that. But other cases, so let me just add to this, plus other cases. I want to talk about those right underneath this as a whole. So when we do that for case 5, we may also need to use a part of these other techniques as well for case 5. So use other trigonometric identities that may be useful, and or use integration by parts, use that, and so this has to do a lot with our individual creativity and how much we remember from previous techniques, frankly. The more you have been reviewing previous material and techniques, the better this piece will fit in your strategy for integrating these expressions too. So manipulate expressions to make them more suitable for integration. More suitable or easier to integrate. Integration, and also there are a couple of formulas that are very, very helpful, and we want to use them often as we have the opportunity. Use the following formulas. So I have a couple of them here, and so integral of tangent of x dx equals natural log of secant x plus c. That's one of the formulas. So we can, if you have an integral of tangent x, you can easily write that down, natural log of secant x plus c. Or if you have an integral of secant x, right, by itself, you can write that as natural log of secant x plus tangent x plus c. These two formulas are going to be very useful for us. Okay. So having talked about these, I think we can then go over some examples here that show us how these work. So that was page 6. So 5 and 6. So this would be page 7. So in this example, we want to evaluate this integral of tangent to the 5th power of x dx. Okay? So let's create, so far, whenever we had this kind of odd power, we always try to create even powers, right? Even with sine x and cosine x, we try to do that. So let's break this apart so that we end up with a tangent to some even power. Of course, tangent to the 4th power x times tangent x. So that would be, and again, as I remember, to remind you to please pause the video, spend 10-15 minutes of your own time to come up with a solution, and then hopefully your solution will match this. If not, you can modify your solution based on this. Okay, so then we begin to do that, what we started to do. So tangent 4x times tangent x dx. And of course, we want to, the purpose of this, breaking this up to even powers, is to make them available to the squared identities we have. So squared identities apply to tangent squared, secant squared, sine squared, cosine squared. So we need to rewrite this again in terms of tangent squared x squared tangent x dx, right? Of course, recall that secant squared x equals tangent squared x plus 1, but we need to rewrite this in terms of tangent squared x. So tangent squared x is equal to secant squared x minus 1, right? Recall that. And now we can substitute for tangent squared x squared with this equivalent. And of course, you know what's coming up next, right? You would pick, after that, after we make that, we substitute for tangent squared x with secant squared x minus 1, then we'll pick u equals secant x. Okay, so we're getting there. All right, so let me do that. We have secant squared x minus 1 squared tangent x dx. Okay. Well, actually now, so this, let's actually expand this to its parts. So we have, so this would be again secant to the 4th power x minus 2 times secant squared x plus 1. All of that times the tangent x we have out here dx. Okay, so let's distribute the tangent x then. So what do we get? We get secant to the 4th power x times tangent of x minus 2. Well, I want to actually, as we distribute this, let's break it apart. So that's easier to integrate. So into pieces. And you'll see why, because now if we do that, we're going to be able to use this integral, one of these formulas. And that'll be nice. So as I'm distributing this into this, I'm going to break this integral into individual pieces. So we'll end up with minus 2 integral of secant squared x tangent x. Oh, I should add dx here, sorry, dx. And then also dx here. And then plus, here's the benefit, one of the key benefits. As I distribute tangent of x to 1, we get integral of tangent x dx, right? We can easily integrate this to natural log of secant x based on one of those formulas that you saw earlier. Okay. So the other thing I want to attract your attention to is that notice, with the exception of this one, which we have a formula to integrate this with, the other two expressions are a combination of even powers of secant x and a single tangent x. Okay? So let's see how we can make use of that. But for now, I just want to make you note of that. We have even power of secant of x times tangent of x, even power of secant x times tangent x. Okay? So now, let's use substitution for both of these, not for that. Okay, so for this, we can write let u be equal to secant x. Therefore, du, it's going to be secant x tangent x. All right? For this one, I'm going to say let w, let's pick another variable, w be equal to tangent x, and dw will be equal to secant squared x dx. Okay? And then that one, well, that one will integrate into, just like we showed using these formulas, that one will integrate to natural log of secant x plus c. So let me write that, natural log of secant x plus c. Okay? I just don't want to be off the screen there. Let me adjust. Okay, yeah, everything's on the screen. All right, so now let's make the substitution based on these new variables u and w. So we end up with, this would be, so if you take a look at that, so if you break this apart into, if you take away one secant of x, multiply it by tangent of x, right? So, well, let me do it this way then. Secant cubed, I don't want to do it, I don't want to combine these two steps, so let me do it in a step. Secant cubed x times secant x tangent x dx. I'm breaking this apart. And I want to keep that the way it is. I think, yeah, this is fine. So I'll just minus 2. At the expense of rewriting this, I wanted to show you how the next step happens by breaking this apart, and then secant squared x tangent x plus natural log of secant x plus c. Okay, now you'll see that how this works. So this would be secant x tangent x would be du, and this piece would be u cubed, right? Do you see it? So now this would be u cubed. All of that would be du. Then minus here, we would have minus 2 integral of secant squared x tangent x. Secant squared x, well, I need to put remember to put my dx's here. Well, they're there too. Okay. So secant squared x dx is equal to dw, and then tangent x is equal to w. So we have w dw. Okay? Pretty easy to integrate that one. I'm sure you can see. Plus natural log of secant of x plus c. All right. So now let's integrate. We have, remember this is these are indefinite integrals, so after we're done with integration, we need to replace u with secant x, we need to replace w with tangent x, okay? Just remember that, because these are indefinite integrals. And so we have add 1, divide this term by the new power 4, like that, minus add 1 to this, you get w squared, divide this by 2, multiply w squared over 2, well, it'll be like this, so times w squared over 2, and then which then they cancel to give us minus w squared, and plus natural log of secant x plus c. Okay, now we can, I guess I can fit that in. I want to simplify this, so this 2 and this 2 cancel out, and we get 1 over 4 u to the 4 minus w squared plus natural log of secant x plus c. And then, of course, we replace back for u and w with the original functions. So we have equals 1 over 4 secant to the 4th power of x minus, for w we pick tangent x, so minus tangent squared x plus natural log of secant x plus c. And there we have our antiderivative here. Okay? All right. I think that would, so that was case 5 and other cases, unless I don't know if I have other examples here. So let's also, in the limited time we have, let's also talk about inverse substitution. That's a neat technique as well. So we have, so this will be inverse substitution. And of course, those of you who have been reviewing from Math 127 or trigonometry class, if you've kept your notes hopefully and book, then that will be handy, using the right triangle. So this technique heavily relies on that. Okay. So this is also has cases, so for inverse substitution. So let me call this, I guess, case 1 again, case A. Let's, because I don't want, we've already gone through case 1 through 5, so let's call this case A. When we have this term in our integrand, a square root of a squared minus x squared. Okay. Here, when we have that, we want to use x equals a sine theta. Notice this is some constant squared, 4 squared, 2 squared, 3 squared, whatever. That's a constant squared minus the variable squared. If we have under a square root, if we have that scenario as an integrand, then we want to use x to be equal to a sine theta. So we'll replace x with a sine theta when theta is, of course, between minus pi over 2 and positive pi over 2. Remember, this is the domain, because in order for a trigonometric function to have an inverse, we want to restrict its domain. Remember that from trigonometry? So within this domain, minus pi over 2 to pi over 2, the sine function is 1 to 1. So it's going to have an inverse. As a matter of fact, let me write that down. So when so you use this when under this condition, when theta is between these two angles, in order to get rid of the root that we have. Rid of the root. So then from here again, all of that, this so this changes, this process, notice that it changes variable x to theta, right? Variable x to theta. So at the end of the solution, at the end of our solution, use sine theta. If you take x equals a sine theta, then sine theta equals x over a, right? X over a and the right triangle translation this, what I mean by that is this right triangle translation of that would be, if this is theta, then this is the opposite divided by the hypotenuse, x over a. And because of this Pythagorean theorem, so this side automatically becomes a squared minus the square root of a squared minus x squared, right? So that's that. And then, so use this and the right triangle translation to return to the original variable x. Variable x. Okay. And note we only have to do this, well, this, if we have an indefinite integral. An indefinite integral. Remember, if you have a definite integral, you simply have to recalculate the limits of integration, and you don't have to go back to the original variable. So this, we will have to do this. We'll have to use the right triangle to go back to the original variable x only if we have an indefinite integral. Okay? So let's call this case A, when we have square root of some constant squared minus x squared. Okay, we have also case A, case B and C. So let's go through all those two other cases before we see an example. I think that's a better approach here. So case B. And what did I say over there? When we have that. So let me use the same thing. So when we have, and I want to highlight this, when we have, that was case A, for case A, when we have that, this time when we have square root of a squared plus, not minus, x squared. Okay, and I want to highlight that that's our case here. And then you want to use x equals tangent theta this time. Where again, we have to restrict the domain of the theta, or this function, where theta is between, because tangent is sine divided by cosine, so cosine is 0 at negative pi over 2 and pi over 2, so theta cannot include those two limits, boundaries, and then off of that, once we have that, then use tangent theta. If you use that, use tangent. Oh, let me also, I forget to put an a here. Use a, sorry about that, a, x equals a tangent theta. Then tangent theta would be equal to x over a, and then use the right triangle translation, which would be this. Tangent is equal to the opposite divided by the adjacent, so this would be opposite. That's the adjacent. That means that by the Pythagorean theorem, we have a squared plus x squared, which is the case that we have. If that's part of our integrand, so now this is the right triangle translation of that, and to return, so we're going to use this right triangle translation to return to the original variable x only when dealing with indefinite integrals. Okay, and let me quickly add case C on the same page. Case C. When we have x squared minus a squared this time. This time the variable squared minus a constant squared. If we have a term like that, and I want to highlight that this is our case here, then we want to use what did we say? So that, okay, so use x equals a, or I should use my blue ink here, x equals a secant theta. Of course, we have to limit the domain of this function in order for it to be 1-to-1. So where theta, secant theta is not defined wherever cosine of theta is going to be 0, because secant and cosine theta are reciprocals of each other. So we have pi over 2 or pi and theta 3 pi over 2. So notice that theta cannot be either pi over 2 or 3 pi over 2, because that's when cosine theta is going to be 0 at those locations. And then from that, this is just a condition. So this goes without, I mean, this is in the background. This is in the background, but the main thing is that substitution. This is in the background. The main thing is that. What we're using to substitute for x is the main thing. And then after that, use secant theta equals x over a, and remember that secant and cosine are reciprocals of each other. And then, of course, let me draw the right triangle translation here. If that's theta, so cosine theta would have been the reciprocal of that. So it would have to be the adjacent divided by the hypotenuse. And then, because that secant is x over a, so cosine would be a over x. And therefore, this piece here would be x squared minus a squared by the Pythagorean theorem, which of course is the term we have if we have this in our integral. And then to return to the original variable x, only when dealing with indefinite integrals. Okay. All right, so now that we've introduced or discussed these three cases, we described them, let's go through a couple of examples maybe and see how this works. So okay. And before that, let me give a couple of notes. I don't know if no space there. So let me give a couple of notes here, very important. Note the restrictions on theta, these restrictions on theta that we mentioned. Theta should be between this and that. And we had this for all these ABC cases. So the restrictions on theta are imposed to ensure, I mean, I said this, but it's better that you have it in your notes, that the trigonometric function is 1-to-1. That's one note we want to have here. And the other thing, to integrate something like this, so if you have that one of those terms, one of those cases, a squared minus x squared, and an x out here, dx, then you don't really need, you can apply that method, but you don't really need to. When to integrate something like this with an x is really the derivative of this. So you take the derivative of the x, you get 2x dx, right? So when you have a derivative of the x variable on the inside, on the outside, what is under the root on the outside, when we have that situation, instead of using the cases, we want to use u equals a squared minus x squared. Okay, and then take the du, you get minus 2x dx, and then you can easily substitute for that. So the whole thing will be u squared. This would be u squared, and you can replace x dx with some factor of du. Okay, that's the point. So if you have the derivative of the x term on the inside, on the outside, you can use this substitution for, you can use this for substitution. Okay, so I just wanted to mention that. So I don't think, even though I have, you can see I have a little bit, more than half a page of space on this page, but I don't think I can fit the whole next example on that. So I'd rather put the whole example, if I can, on one page. So I'm going to move to the next page, and that would be that. So suppose we want to integrate this expression, dx over x squared times 4 minus x squared. Okay. All right. So considering, still, even though this is the first example of this kind, I recommend that you spend 10-15 minutes and see what kind of solution you come up with, and then come back to the video after pausing it for a few minutes. So considering, and I'm hoping you've done that, and now you're back. So considering that we have 4 minus x squared, this is one of those cases that says a squared minus x squared, right? So considering 4 minus x squared, then let x be a, so 4 would be 2 squared, right? So a would be 2, so x would be 2 sine theta as a substitute for theta ranging between negative pi over 2 to pi over 2. If that's the x, then we can quickly say then dx is 2 cosine theta d theta, right? That's the derivative of that expression on both sides. So now let's see what we can substitute this for. So I'm just going to start with that. Therefore, we start with 4 minus x squared. So this would be 4 minus, if we substitute 2 sine theta for x, we get 4 squared, x squared, we get 4 sine squared theta, right? So minus 4 sine squared theta. Then factor the inside. Like that. And of course, you're familiar with what this is. This would be 4 times cosine squared theta, right? And this is square root of 4 cosine squared theta. So we'll end up with 2 cosine theta, right? So this would be equal to 2 cosine, well, absolute value of cosine theta, but cosine theta between these two limits, when theta is between negative pi over 2 and pi over 2, which swings back and forth between the first and the fourth quadrant, cosine of theta is positive anyway. So we don't need those absolute value symbols. So equals 2 cosine of theta. Okay. And for when theta is between those two angles. All right, so now what we ended up with is we found an equivalent for square root of 4 minus x squared is equal to that. So we can substitute for the rest of that with what we have here. So x squared would be 4 sine squared theta, and all of that would be replaced by 2 cosine theta. So let's replace where everything we have here with their equivalents in terms of theta. And when I do that, I know it's off the screen, but let me see if I can keep everything on the screen. I don't think so, no. So, but I'll post these in Canvas so you can download these lecture notes anyway, so that so no worries there. So, well, or I can rewrite the expression here so you can see it. So we start with dx over x squared square root of 4 minus x squared, and then equals the dx is 2 cosine theta d theta. So I'm going to replace it with that, 2 cosine theta d theta divided by 4 sine squared theta. That's when you replace x squared with 2 sine theta, you get 4 sine squared theta. So 4 sine squared theta times this equivalent of that in theta, which is 2 cosine theta. Okay, so now what do we have? We have 2 over 2 times 4, 8, so 2 over 8 or 1/4. So let's simplify this. 1 over 4 times integral of, if we simplify things, that's cosine squared theta. Cosine and cosine cancel out. We get 1 over sine squared theta d theta. So we get 1 over sine squared theta d theta, right? After simplifying terms. And then 1 over sine squared theta is it's cosecant squared theta, right? Cosecant and sine are reciprocals of each other. We learned that back in trigonometry class. So 1/4 times cosecant squared theta d theta. And we know that if you integrate cosecant squared theta, you get minus cotangent theta. Okay, so this will be, we can immediately integrate this actually. So we get minus 1/4 cotangent of theta plus, because this is an indefinite integral, so we get c. So notice that this is this was an indefinite integral. So because we started with an indefinite integral, we'll have to convert back to x, and we're going to use that. So we started with x equals 2 sine theta. So sine theta is equal to x over 2, right? Let me write that here. X equals 2 sine theta. 2 sine theta. Therefore, sine theta is equal to x over 2. And from here, we can translate this into right triangle theta. Sine is always opposite divided by the hypotenuse, so, or x over 2, which means this side, by the Pythagorean theorem, is equal to 4 minus x squared. Okay? Now, knowing that, we can replace for cotangent theta, because cotangent of theta is adjacent divided by the opposite. So therefore, I'll just put an arrow here and do that. So then we can write, minus 1/4 minus 1 over 4 times cotangent theta, adjacent, divided by the opposite. So square root of 4 minus x squared over x. And then, of course, plus c. And then, of course, this is minus all of that, 4 minus x squared divided by 4x. 4x plus c. And that would be the final result of this antiderivative. Okay? So let's do another example. I think it would benefit us if we did that. And so suppose we want to integrate dt divided by t squared square root of t squared minus 16. So this is variable squared minus a constant squared. Okay. Again, please give it your own thoughts to this for 15 minutes. Write down a solution and then come back to the video. So considering that we have that term, right? So we want to let t be equal to 4 secant theta. This is one of the cases we have, right? Whenever you have a variable squared minus a constant squared. So you use a, in this case, a would be 4, because 16 is 4 squared, so a is 4 secant theta. For, of course, theta has to be within a certain limit when it's defined, or when we have this function as a one-to-one function. So pi over 2, or theta being between pi and 3 pi over 2. Okay, so if we have that, then of course the d theta, dt will be 4 secant theta tangent theta d theta. Okay, that's the derivative of both sides. So therefore, then let's rewrite this. So therefore, we have given square root of t squared minus 16. We can replace it by t would be 16 secant squared theta minus 16. And then so factor this out. We get 16 times secant squared theta minus 1, right? And then, of course, this is, we know this from squared identities, this is tangent squared theta, right? So this is equal to 16 tangent squared theta, and therefore we have 4 tangent of theta. So this is equal to square root of t squared minus 16. We found an equivalent for it. Okay, so now we can. So this is for the relevant values of theta, for relevant theta, of course, like that. Okay, so now we can rewrite the original integral. We started with this, dt divided by t squared times square root of t squared minus 16 equals, so we have 4, I'm just substituting for dt with that expression, 4 secant theta tangent theta d theta, and also in the denominator, for t squared, I'm going to substitute 16 secant squared theta. And then for that whole term, for square root of t squared minus 16, we have this, 4 tangent of theta. Okay, so all of these terms simplify quite a bit, right? Tangent theta cancel out, 4 over 16. So let's see what do we end up with. After simplifying, and this 4 cancel out, we get 1 over 16 times integral of 1 over secant theta d theta. Okay, and of course this is, I'm sure you know, this is simply cosine theta. So 1 over 16 integral of cosine of theta d theta. And of course this is 1 over 16 sine theta plus c. Of course, this was an indefinite integral. So we need to go back, we need to use the right triangle translation to go back to the original variable t. So to do that, because we took t to be 4 secant theta, therefore secant theta is equal to what? T over 4, right? T over 4. So the right angle translation of this, therefore, right triangle translation would be, if this is theta, and we know that the reciprocal of this would be cosine theta, and that would be 4 over t, so t would be the hypotenuse, 4 would be the adjacent for cosine theta, and this side would be t squared minus 16. So that, like that, t squared minus 16, which is the term we originally had in our integral right there. Okay, so now we can replace back. So therefore, and from here, then we can come up here and say, so this was where we ended up with. So now we need to replace sine theta with something that is in terms of t, because we have an indefinite integral. So we have 1 over 16 sine theta, according to our right triangle translation, would be the opposite divided by the hypotenuse. So we have times square root of t squared minus 16 divided by the t plus c, of course. And then, so we get square root of t squared minus 16 over 16t plus c, like that. Okay, I think we have time. We barely have time for one last example. So, and when I say this, I mean this equipment in less than half hour, it'll turn off automatically. So that's why there's a limited time on it left. So, so let's get through that example as well while we have time. So here, this new example, this is kind of a new example. So sometimes when we have terms like this, x squared plus a squared, of course that's when we have, in the cases that we looked at, that's when we use x equals tangent theta, right? That when it's under the square root. But this is also n over 2. Okay, so n over 2 or x squared minus a squared over n over 2, or to n over 2 power, which I believe this was, let's see, which I think was, that's the secant, when we did the secant, or the other one. So let's see, which one was that? So that's when, yes, that's when we use secant. This is when we use the tangent. Okay, x equals a tangent theta, and here x equals secant a secant theta. Okay, so we can also use that when we have a square root raised to some other power. Okay, so let's see what we mean by that. Okay, here's an example. So we want to evaluate from 0 to a this integral dx over a squared plus x squared. See, that'll be x equals a tangent theta, right, because of this, to 3 over 2, and where, of course, a is greater than 0. Okay, so note that first thing, note that a squared plus x squared to 3 over 2 power, we can rewrite that as square root of a squared plus x squared cubed, right? So based on that, we want to let x be based on the inside of this term, inside this parentheses, or under the root here, we want to let x be equal to a tangent of theta, which means immediately that dx is equal to a secant squared theta d theta. But this is, remember that this is a definite integral, so we need to convert to these limits to the limits that are appropriate for theta. So if, or let's see, so if x, so if x equals, let's say 0, if x equals 0, right? If we, in this equation we substitute for x with 0 the lower limits of integration, then we're going to get tangent of theta equals 0. But when is tangent of theta equals 0? When sine of theta is equal to 0, because tangent theta is equal to sine theta divided by cosine theta. And we know that that happens at when theta equals 0. So when x equals a, we have tangent of theta. So substitute for x with a here. A's cancel out. You end up with tangent of theta equals 1. When is tangent of theta equals 1? It's when theta equals pi over 4. Right? So these are the new limits of the integration. So we can rewrite. So we started with this. We start with 0 to a integral of dx over a squared plus x squared. I'm rewriting it because it's off the screen. Like that. Then we go from, well, let's actually rewrite this in terms of the square root. So I'm just going to rewrite this. So 0 to a dx over square root of a squared plus x squared cubed, right? Now let's apply the new limits of the integration. 0, and I'm going to have to use a next page for the rest of the solution of this. So dx was equal to a secant squared theta d theta. So we're going to replace that with its equivalent in terms of theta and d theta divided by, let's replace a squared. Well, a squared is a squared, but then x squared is going to be replaced by a squared tangent theta squared. Like that, cubed, right? So now the inside, we can factor this out. I think you see where this is going, how it's going to simplify. So let's factor the inside. We have a squared times 1 plus tangent squared theta cubed. And we know that 1 plus tangent squared theta is secant squared theta, right? So let me put this here. And so we have 0 to pi over 4. Trying to keep everything on the screen there. And so we have a secant squared theta d theta divided by, let's see, like that. So we have like this, a squared secant squared theta cubed. Okay, great. So we don't need that anymore. Like this. All right. So we have, so we can simplify this because this is all square root of something. Both terms are squared, so we can remove the root from at this point. Like that. So we have a secant theta cubed. Okay. And then we can distribute this power to everything here. So let's do that. And when we do that, well, let's do it step by step. So 0 pi over 4, a secant squared theta d theta divided by a squared, a cubed secant cubed theta. Now you can see that this a and this a cubed kind of simplify each other, and then we can pull them out of and place it in front of the integral. So we get 1 over a squared integration from 0 to pi over 4 of, this is simply 1 over secant theta d theta, right, after simplifying, and that's cosine of theta, right? So we have 1 over a squared from 0 to pi over 4 cosine of theta d theta. Of course, this integral is pretty easy. We can say 1 over a squared times sine of theta going from 0 to pi over 4. Okay, then we apply the limits of the integration, and what do we get? We get sine of pi over 4 minus sine of 0. Of course, that drops out. We get 0 there, right? So this is just 0. Sine of pi over 4 is square root of 2 over 2. So let's equals 1 over a squared times square root of 2 over 2. And what do we end up with? We end up with square root of 2 over 2a squared. Like that. Okay. So this was one of those cases that might come up where you have a square root raised to some other power, 3, 4, or higher power. So thank you for watching the video until the end. I hope it was worth your time. If you have any questions, I trust that you will come to me. So for now, have a nice day, and I'll see you again next time.